We often get caught up in the complexity of things, right?
Yeah,
But, sometimes it's the simple molecules that are the real MVPs,
absolutely.
like ammonia,
Yeah,
just NH3, but it's everywhere,
it really
From
is.
the fertilizer that helps grow our food to some of the cleaning products we use.
Hmm.
It's a it's way more fundamental than it might seem at first glance, and that's why we're taking a deep dive into it today.
That's right. We're going to be exploring ammonia, how it's made, what its properties are, and why it's so incredibly useful.
Exactly. And for this deep dive, we're going to be using a grade 12 chemistry textbook as our guide.
Yeah, it's a great resource. It's got a lot of really solid information about ammonia.
Yeah, so consider this your crash course on the essentials of ammonia.
Right.
All right, so let's get started. How do we actually produce the vast amounts of ammonia that the world needs?
Well, the textbook highlights the Haber-Bosch process as the main method for producing ammonia on an industrial scale. And it's this really elegant piece of industrial chemistry where you're essentially taking nitrogen gas, which is all around us in the air,
Right.
and combining it with hydrogen gas, which is often derived from natural gas, to form ammonia, which is NH3.
And I remember seeing the balanced equation for that in the textbook, N2 gas plus 3H2 gas, and that's in equilibrium with 2NH3 gas.
Exactly. You got it.
So it's not as simple as just mixing those gases together, right?
Mm.
The textbook talks about Le Chatelet's principle and how specific conditions are needed to get a good yield of ammonia.
Yeah, that's a really crucial point. So Le Chatelet's principle basically tells us that if you disturb a system at equilibrium, say by changing the pressure or temperature, the system is going to shift to counteract that change.
Right.
And in the Haber-Bosch process, we want to shift that equilibrium to favor the production of ammonia.
Of course, yeah.
So one way to do that is by increasing the pressure, because the reaction actually reduces the total number of gas molecules. You're going from 4 molecules of reactants to 2 molecules of product.
Right.
So cranking up the pressure really pushes that equilibrium towards the ammonia side.
So high pressure is key for getting a good yield.
Absolute high pressure is essential.
Now, what about temperature? Because I remember the textbook mentioning that while heat is involved,
Yeah.
it's not the main factor for maximizing yield, and that seemed a little counterintuitive.
Yeah, that's an interesting point. So there's this interplay between thermodynamics, which tells us how much ammonia we could theoretically make,
Right.
and kinetics, which tells us how fast we can make it.
Mm-hmm.
Now, lower temperatures would actually favor ammonia formation because the reaction is exothermic, meaning it releases heat.
Okay.
So if the reaction's producing heat, it doesn't want to be in a hot environment.
And wants to cool down a bit.
Exactly. But here's the catch. At lower temperatures, the reaction would be so slow, it'd be like watching paint dry.
Oh, wow.
Yeah, and that's where the catalyst comes in.
Wow.
The textbook mentions a finely divided iron catalyst, which speeds up the reaction to a practical rate. And this catalyst works best at elevated temperatures, but not so high that we shift that equilibrium back towards the nitrogen and hydrogen.
Right, so it's like a balancing act.
It is the balancing act.
You need the high pressure to get a good amount of ammonia and the catalyst to make the reaction happen at a decent speed, and then that moderately high temperature to keep the catalyst happy.
Exactly.
I like how figure 3.2 in the textbook gives us a visual representation of this whole setup. You can see the nitrogen and hydrogen going in, passing over the catalyst in the reactor, and then that ammonia being collected by cooling it down in a condenser.
Right.
And I also noticed they recycle the unreacted gases, which seems like a smart way to make the process more efficient.
Yeah, definitely. It's a very clever and optimized industrial process.
Okay, so we've made the ammonia.
Yeah.
What are some of its key properties? Like what makes it behave the way it does?
Well, the textbook outlines some important physical properties.
Yeah.
For starters, ammonia is lighter than air. It has a density of about 0.769 kilograms per cubic meter at standard conditions. And it's commonly available as a 28 to 30% solution in water.
Right.
Now that aqueous solution has some interesting properties too.
Yeah, like what?
Well, ammonia partially reacts with water to form ammonium ions, NH4+, and hydroxide ions, OH,
Yeah.
which makes the solution alkaline.
Right. And that ties into its solubility in water, too.
Yeah.
I think activity 3.4 in the textbook asked about that. The fact that ammonia can form hydrogen bonds with water along with that ionization makes it really soluble.
Exactly. And speaking of properties, we can't forget about that pungent odor.
Yeah, experiment 3.1 reminds us that ammonia has a really strong smell and it's also toxic.
Mm-hmm.
So those are definitely things to keep in mind when handling it.
Absolutely. Safety first.
So experiment 3.1 also demonstrates another important chemical property of ammonia, its ability to react with acids.
Right.
When you bring ammonia gas near concentrated hydrochloric acid, you see those characteristic white fumes.
Yeah, those white fumes are actually tiny crystals of ammonium chloride forming from the reaction of the ammonia gas and the hydrogen chloride gas that's coming off of the acid.
Interesting. So that's a good example of ammonia's basic nature because it's neutralizing that acid.
Exactly.
Okay, so we've covered the industrial production and some of the key properties, but what if you wanted to make a small amount of ammonia in a lab setting?
Well, experiment 3.1 in the textbook actually covers that too.
Oh, perfect.
The typical lab preparation involves heating a mixture of ammonium chloride and calcium hydroxide,
Okay,
and the heat drives a reaction that produces ammonia gas along with some calcium chloride and water.
got it.
And the textbook also mentions that you can use calcium oxide as a drying agent to get pure dry ammonia if needed.
So how do you know if you've actually produced ammonia gas in the lab?
There's a simple test described in experiment 3.1. You take the gas that's being produced and you hold it near some concentrated hydrochloric acid. And if you see those white fumes of ammonium chloride forming, then, you've got ammonia.
Oh, that's pretty straightforward. And I remember the textbook also showing the fountain experiment in figure 3.6b. That's a pretty cool way to demonstrate some of ammonia's properties.
Yeah, it is. It's a really neat visual demonstration that shows ammonia's high solubility in water and its alkaline nature all at once.
So how does that experiment work?
Well, they take a flask filled with ammonia gas and they flip it upside down into a dish of water that contains an indicator like phenolphthalein.
Okay.
And because the ammonia dissolves so easily in the water, it creates a lower pressure inside the flask, which sucks the colored water up, and you get this fountain effect.
Wow, that's pretty cool.
Yeah, and the phenolphthalein turning pink shows you that the solution is alkaline.
Well, thanks for joining us for this deep dive into the fascinating world of ammonia. We hope you found it illuminating.
Thanks for listening.
And we'll see you next time.
See you then.